Alright, we did it! In this series on functional programming, we are past the lobby where we were convinced why we should use functional programming. We consulted the floor directory with the principles of functional programming we'll be discovering throughout the series. And now we've finally pushed that elevator button, entering into the ground floor with purity. For the next few episodes, we'll work with this example. We have a cookie machine which gives us random cookies, and we'll be visiting it to build up our collection of cookies. This is a decidedly silly example, but it's analogous to many real-world things. It could represent querying a paginated endpoint, doing a bunch of operations in parallel in batches, reacting to user input, for example, collecting all the keys typed into a search box, pinging a single service or system or multiple services or systems for their status, checking and waiting for some async operations to have completed, etc. For the time being, our example is synchronous, but later on in the series you'll see how we can use the same code to deal with synchronous or asynchronous things. The world we're modeling is interacting with a cookie machine, which makes me make sense. As of now, I've written the function this way. First at the top, we simply define all the cookies our machine could possibly give us. For now, to keep it simple, we'll just have chocolate chip, oatmeal raisin, and snickerdoodle. And if those aren't your favorite kinds of cookies, well... But make a case for your favorite cookie in the comments and we can change the example going forward. This function here, called collect, is how we collect the cookies from the machine. The implementation's not super important, it basically just returns one of those three types of cookies at random each time you call it. And this function, visitSingle, is a program mimicking what happens when you go to this machine and get one cookie. You give it your current array of cookies, it calls the collect function to get a random cookie from the machine, and puts that new cookie into your collection. Translating this to more realistic application code, the collect function is like the API, system, service, or stream of user input that we're interacting with, and the visitSingle function are the network requests, operations, and logic we're executing to process that thing. Really let that sink in. The power of FP is in finding patterns and applying solutions to multiple different use cases. So this funny example translates well to many situations you'll encounter in real-world software engineering. Simple enough. Let's test it. The tests are also pretty simple. Up at the top, we initialize our initial collection of cookies, which is empty to start. On this line, we visit the cookie machine one time and save the resulting cookies that we got into a variable. And now we want to test that what we got back matches what we expected to get back. But the first annoying thing with testing is that because of the randomness, we have no idea what cookie we expect to get back. So while I would love to assert that we got back a chocolate chip cookie or whatever, we don't know if that's what's going to happen. The only things we can really do are check that the resulting collection of cookies we got back is exactly one cookie. And if we want to be a little more rigorous, we can check that the cookie we got back is one of the valid types of cookies. Hopefully our machine didn't just make up a new cookie and spit it out. Okay, so now I want to run a different scenario and test that. This time we're going to visit the machine twice. We'll call visitSingle with our initial collection of cookies and get our first visit cookies. Now we can check that the collection of cookies we got from that first visit should have exactly one cookie, and that it is one of the three valid cookies. Then we visit the cookie machine a second time and save that result to a second variable called secondVisitCookies. And once again, secondVisitCookies should have length 1, and the cookie in it should be one of the three valid types. But we've already run into a problem because that first visit we were only supposed to get back one cookie, but it says we got back two? Turns out the issue is because our visitSingle function is a mutating function. There are also a few other issues, like the randomness, but we'll be dealing with those later. In this episode, we're going to fix this with immutability. Let's get into it. First off, a puzzle. I have this function which will add a number to another number. I also have this function which will add an element to the end of an array. How are they different? Let's see the difference I'm trying to get at with a few tests. Consider this test case of our sum function which adds two numbers. We'll start with our two inputs a equals 2 and b equals 3. We'll store the output of the function on those two values into a variable called result. If you're old enough to watch this video, you probably know that the answer is 5.
You went to 4 years of college and 4 years of medical school, so I can safely presume that you are at least 8.
And as a side note, a is still 3 and b is still 2. Great. Now let's test our append function, which adds an element to the end of an array. What'll happen this time? We'll start with an input array A, which is set to 2, 3. The value B will be set to 4, and we'll store the result of adding B to the end of A into a variable called result. And as expected, result is an array containing all values 2, 3, 4. Cool. So far so good. And as a side note, B is still equal to 4, and A is equal to... A is no longer equal to 2, 3. What? When I first learned this in school, I was like, what the hell is this? Code sucks and it's a lie. To me, it's like if I sat down at a restaurant and saw a little dirty spot on my plate and asked the server to replace it, and then I found out that all they did was go to the back and lick that plate clean and hand it right back to me. I mean, it's an efficient strategy. Reduce, reuse, recycle after all. But I mean... Turns out this is related to mutability versus immutability.
Hey, that's the name of the show.
Pass by reference versus pass by value. They mutated my plate rather than replacing it. Something different is happening in these two functions, and it has to do with how the language handles different types of data. Let's trace through what's happening in those functions when we call them. The add function is very simple. When we call it, a copy of each input is made. In the example from before, we get a local copy of A with the value of 3, and a local copy of B with a value of 2. Then we add those two together to get a new value 5, which we return out of the function. Outside the function, we receive the value and assign it to the variable called result. This is called pass by value, because we are copying the actual value of the variable when we go into and out of a function. In JavaScript/TypeScript, primitive types are the ones that are passed by value. These are mainly strings, numbers, and booleans. However, arrays are not primitive types, and they are passed by reference. Going back to the previous example, when we set the variable a to an array of 2, 3, we're actually creating a new place in memory with the list 2, 3, and storing a reference to that place in memory in the variable a. This is an important distinction. A is not itself the value 2, 3, but rather a reference to the place in memory where that value is stored. So in our append function, when we get a local copy of this first variable array, we don't get the values 2, 3. We actually get the reference to where that value is stored. The second argument is just the plain number 4, which is a primitive and it's passed by value. So our local copy of that value is actually the value 4. Now when we call array.push, we are modifying that actual location in memory to append that value to the end of the array. Most importantly, all the references still point to this same place in memory. In other words, we have modified or mutated that input value. Now from this function, we return another reference to that same place in memory. So back on the outside, we take this reference to an array and store it into the variable result. At this point, notably, both the variable a and the variable result are references to the same place in memory. That's why when we expect the variable result to equal 2, 3, 4, it does, because it's a reference to the place in memory where a list is stored with the value 2, 3, 4. However, confusingly, the variable a still references that same place in memory. So when we expect a to equal 2, 3 like it did before, it doesn't. The array that it's referencing has been modified to equal 2, 3, 4. In other words, result and a are just aliases for the same bit of data, and we've mutated it. All they did was go to the back and lick that plate clean and hand it right back to me, and lick that plate and hand it right back, and lick that plate and hand it right back, and lick that plate and hand it right back. This is all enabled by the fact that arrays are passed by reference. But it's also because of this suspect function array.push. This is a standard JavaScript function that mutates an array by adding a new thing to the end of it. Most notably, it does not give you a new array with the values copied over and the new thing added on. Instead, it actually modifies the array that you gave it and just gives you a new reference to it. So a data structure is mutable if it can be mutated by a mutating function that mutates its input by causing mutations that mutate it. Oh, English, what are you doing? Or we can get past all of those stupid words by using immutable data structures.
That's the title! They can't cut that!
I.e., ones that are not mutable. So in plain English, a mutable data structure is one that can be modified in place. An immutable data structure is one that cannot be modified in place. Every time you make an update to an immutable data structure, you copy it over and return a new data structure with those changes. A mutating function is the other side of the coin. It's a function that modifies its input by mutating it, i.e. changing it in place. A non-mutating function, i.e. a pure function, does not do that. It leaves its inputs untouched, and if it wants to make changes, it does so by returning a new piece of data with those changes. Pass by value means that when a variable is passed into a function, the value itself is copied into that function. This happens by default for the simple types, aka primitives, like booleans, strings, and numbers. Because these types are passed by value, functions that accept them as arguments are not even able to mutate those inputs if they wanted to, because they get an independent local copy, and any changes made inside the function will not be reflected outside. Pass by reference, on the other hand, means the function does not get an independent copy of that value, but rather gets a reference to where that value is stored in memory. This means if the function's being bad, at least in functional programming terms, it can modify that place in memory, and those changes will be reflected outside of the function. Let's update the function to look like this. Now we're taking advantage of what's called array destructuring in JavaScript. Here's how it works. Inside this function, the first argument is still passed by reference because it's an array. We get a reference to wherever this array lives in memory. Now, in this single line of code, a lot of things are happening, but effectively, this is what we're doing. The brackets create a new place in memory to store a new array. The ... array syntax is array destructuring, and it says copy over the values from the original array into this new location in memory. And then we just tack on the last thing to the end of this new location in memory. We return the reference to this new array that we've created. Now on the outside, we take that reference and store it to the variable result. At this point, the variables a and result actually point to two different places in memory. And that's why when we expect result to equal 2, 3, 4, it does, because it's pointing to the new array we created, which has that extra element added on to the end. And the variable a is pointing to the old location in memory, which we've left untouched. So it still equals 2, 3. Okay, so back to our cookie machine example. What was going on there? Well, the problem was this variable, myCookies, we initialized in a global place that was shared between those two tests. And because our visit single function from before was mutating that collection, the first test ran and mutated that array, and then by the time the second test ran, it already had one cookie in it because it was polluted from the first test run that put a cookie into it. So this assertion in the second test assumed that we visited the cookie machine once and we should only have one cookie. But unbeknownst to it, the previous test had already added a cookie, and that's why it had a length of 2. These kinds of data pollution issues happen all the time in tests, and it makes them very hard to fix because it often depends on the order the tests are run, and the link between them is not clear at all. It's completely implicit. So the obvious, common, easy band-aid fix is just to move that initialization into each test independently. So here, instead of initializing myCookies outside of the tests where it's shared by both of them, we move this line into each test. Now, each test is independently initializing an empty collection of cookies that we start with and runs through all the logic. That means the test can know for sure that it is indeed starting with an empty collection of cookies. But of course our second test still doesn't really work because the two visits to the cookie machine depend on each other. Here we're expecting that the second visit only gets one cookie, but the second visit is just a reference to the array from the first visit and it's been polluted, so it actually has two cookies. The one from the first visit to the machine and the one from the second visit to the machine. You could say it's not a big deal. You visit the machine once and then you get one cookie, and visit the machine again, and now you have two cookies. But I really don't like this implicit dependence on each other, and the fact that you need to test the results of that first visit to the cookie machine before you visit the machine a second time. This means that our program code that visits the machine twice is intermixed in there with all the testing assertion code, so it's kind of hard to read in my opinion. So let's fix this with the star of today's episode, immutability. So here's a file that does things a little differently. Up at the top, the cookie machine code remains exactly the same. It still returns one of those three types of cookies at random every time you call the collect function. But here, our visit single function has changed. it no longer accepts your collection of cookies and modifies it. Instead, it doesn't care what cookies you have already, it just returns you a new collection of cookies. In this case, that means getting a cookie from the machine and putting it into an array with a single cookie in it and returning that new array back to you. And now our tests, in my opinion, are a lot simpler. The first test simply visits the cookie machine once and returns whatever we got from that single visit into a variable. And then we do the same assertions. There's one cookie and it's a valid cookie. The second test is shuffled around a bit. Now we visit the cookie machine 2 times at the very beginning of the test. We save the results of each of those visits into its own variable. And now we're done doing all the stuff we want to test and we can move on to actually asserting stuff about what happened. This creates a very nice separation between what you're testing and how you are testing it. And now, since those 2 visits are independent, we know for sure that they each have a length of 1 because each visit only gives us 1 cookie. If we do want a single collection of all the cookies we've received, we can do that explicitly by merging them all together like this. This was effectively what was happening before, but it was all kind of hidden from us and we had to know that that's the behavior of the function. Here, it's very explicit that we're putting those collections together and they remain all independent. We still maintain the collection we got back from the first visit, the collection we got back from the second visit, and now this new collection of all the cookies we got from all visits. And merging them all together is our concern. That's something we want to do, not something the function should really have to care about. And notice, by the way, it's almost impossible to make the mistake that we did back at the beginning of the video. That data pollution issue between both of the tests was kind of just an indication that something was off with our design. So here, by using immutability, not only have we fixed the test issues that we had before, but we've made it much harder for the caller of our functions to mess things up, and in my opinion, we've made the test a lot clearer and easier to follow. So you can see what Purity does for making your programs conceptually easier to follow. Impure functions can look like this. You pass some data in, and it might give you some data back out, but also on the side, maybe it's changed a bunch of stuff and you didn't really know about it. Pure functions, however, are very simple. You pass data in and you get data out. You know exactly what's happened, and importantly, that nothing else has happened. Your program becomes a simple sequence of snapshots of the state of your program, like multiple images coming together to make a movie. So this is a definite improvement to our code from the beginning of the video.
But there's a but.
Why do I feel like there's a but coming?
But things are definitely still not perfect. We still have that randomness in our cookie machine, which means that the best we can do is test that we only get 1 cookie back every time. I want a lot more control over my code and a lot more assurances that it's doing exactly what I expect. We will be coming back to this example throughout the rest of the series, adding more and more features and using more and more powerful concepts to keep the code simple. In the next video, we'll extend our example to highlight how bad that randomness problem is, and then we'll solve it. We're maybe 10% through the episodes I have planned and like 1% through the code awesomeness. So if this has all been a recap for you, stick around a few more episodes and check out where we end up. And of course, don't forget to like and subscribe and hit that bell so you don't miss the next video. And until next time, take care and see ya.